So we are at the data link layer whose role is frame by frame delivery. As part of this, it provides many services. In this video, I will provide an overview of one such service, error control. The details will follow in other videos. Now, what is error control? Errors are nothing but altered bits. For example, if the transmitter were to send a 1, the receiver incorrectly decodes it as a 0 and vice versa. Error control refers to detecting such errors as well as recovering from such errors. Now, what do you think causes errors? We have covered this before. Errors are caused due to distortion of signals due to frequency dependent attenuation or noise. We covered all this as part of the physical layer. There are two types of errors, single bit random errors and bursty errors. Suppose if this were the transmitted sequence, in single bit random errors, each bit is in error with a certain probability, let's say 10 to the power of minus 5. So at the receiver, I'm just assuming this bit is in error and rest are all fine. So this is what you're going to receive. In bursty errors, a bunch of bits that are adjacent to each other will be in error. So in this case, what the receiver will see could be something like this. So this bunch of bits are in error. So this is the case of a bursty error. I think you will relate to this better through this example. Suppose you have a noise spike that lasts for 1 microsecond, and let's assume that this noise spike causes errors in the data stream. Suppose the data rate is 1 Mbps, how many bits do you think will be in error? So 1 Mbps boils down to 1 microsecond bit duration. If you assume that this noise spike overlaps this bit duration exactly, then this is going to produce single bit errors. Now suppose the data rate is 100 Mbps. How many bits will be in error now? That's right, this is going to produce a burst error of 100 bits. Errors are a reality, you can't escape them. Now, should we bother detecting them? Data fidelity is a very important concern. In other words, you want your data to reach the other end intact. Suppose you are an e-commerce company and you send this statement as part of the email, and let's say due to errors, the P became T. Now, this is something which you would not want to happen, right? So it's important to detect errors. So apart from data fidelity, is there any other reason why you want to detect errors? Another reason to detect errors is to prevent wastage of resources. What do I mean by this? Suppose you have a packet that has to travel many hops to reach the destination. Now, if this packet suffers an error in the very first hop, there is really no point in transmitting over many hops and wasting the bandwidth at all these intermediate links because it is anyway in error. So it's useful to detect errors, and let's say because of this, we put in mechanisms in place to detect errors. Now, what do you do after detecting errors? You could just drop the frame. What are you seeing? How can that be okay? Ethernet does just that. When error rates are small, you could delegate the responsibility of recovery from errors to some higher layer protocols like TCP, which will recover the losses, so it's not your headache anymore. Or in certain cases, like in the audio applications, a few losses don't hurt the application. In other words, you cannot really make out that anything went wrong. Even if something went wrong, you can rely on the human protocol there to recover the errors. Basically, the person can say, can you repeat that please? I couldn't follow what you said. Something like that. On the other hand, if you think that it is important to recover the frame because the loss rates are high, you could employ two mechanisms. One is called error correction, where the frame itself carries enough information that you can correct the errors. The other is retransmission, where you detect the error but you cannot really correct it, in which case the receiver signals the sender that it has seen an error, and then the sender is going to retransmit the frame. This I'm calling it as retransmission. So here are a few things about error correction and retransmissions. In error correction, typically requires a lot more bits to be sent as part of the frame than error detection. In other words, both error correction and error detection need some bits to be sent as part of the frame to do the correction or detection, but correction typically requires more bits. And another point to note is that these redundancy bits are sent all the time. In other words, every frame carries these redundancy bits. On the other hand, the retransmission requires another copy to be sent only on error. In other words, you don't retransmit unless there is an error in the frame. So given this, if the losses are extremely rare, which of these mechanisms would you employ? Error correction or retransmission? Retransmissions, right? Why send all these redundant bits all the time, these extra redundant bits needed for error correction all the time when errors are so rare? You might as well recover from that rare errors by asking the sender to send the copy again. So error correction is useful typically when the error rate is very high, in which case you don't want to retransmit each and every copy. It's good to send the redundant bits so that you can kind of recover it. It is also useful when the cost of retransmission, by here cost I mean, for example, the latency of retransmission is too high. This can happen in a satellite link. You don't want to wait for a really long time for the copy to come. So you might as well send some error correction bits so that you can recover the error. And error detection is naturally useful for the opposite scenarios. That is when the error rate is low and the cost of retransmission is not high. Both error detection as well as error correction employ the following framework. Basically, you add some redundant information to a frame to detect or correct errors. Typically what happens is at the sender you add k bits of redundant data to m bit message. This k is derived from this message through some algorithm. We will cover some algorithms shortly. At the receiver, you reapply the same algorithm on the m message bits to recalculate k and do a comparison to figure out whether the frame is in error or not, and then take a corrective action. So in detection, for example, which Ethernet does, this k is much smaller than m. So for example, Ethernet uses 32 bits for a message of duration roughly 12,000 bits. On the other hand, this error correction codes, they have what is called a code rate, where m is the amount of useful data and this is the total data. So this says what is the portion of the received data that is useful. So for example, in Wi-Fi, these code rates vary from half to 5/6. When it is half, that means you're adding one redundant bit for every bit. And if it is 5/6, that means you are adding one redundant bit for 5 bits. So as you can see, for error correction, the amount of redundancy you add is significantly higher than that of detection. So an important question here is, how are these algorithms that detect and correct errors work? So before we get into the details, here is some theory. Hamming distance is an important concept that captures the error correction and detection capabilities of a code. So in this context, m message bits, when you add k redundant bits to it, this combination is called a code word, and here I have set it to equal to n bits, where n is equal to m plus k. Now Hamming distance is nothing but the number of bits two code words differ in. You can obtain it by XORing the two code words. So for example, if these are the two code words, what do you think the Hamming distance is? That's right, 5. An algorithm translates the m message bits to an n-bit code word. Now there are 2 to the power of n possible code words. Out of these 2 to the power of n code words, how many are legal code words? By legal, I mean actually get transmitted. This is only 2 to the power of m because you have m message bits. That means you have total of 2 to the power of m messages, and each of these messages gets translated into a code word, distinct code word. Thereby you only have 2 to the power of m legal code words. An algorithm basically translates these messages into code words, and this is called a code. That is, the legal code words form a code. Now Hamming distance of a code is given here, where among the list of legal code words, take all combinations of two code words, find the Hamming distance, and the minimum over all of these is the Hamming distance of the code. So what this basically means is that any two code words that are part of this code differ by a distance of at least d. That is what it means. So the error detection and correction capabilities are a function of the code's Hamming distance. Let me reiterate this once more. So when a code has a Hamming distance of d, that means that any two code words that are part of this code will differ by a distance of at least d. So given this, how many errors do you think you can detect for a code whose Hamming distance is d? I want this as a function of d. This is not that difficult to solve. Think carefully. So the answer is d minus 1. Basically, you won't be able to detect an error if one code word got converted into another code word, and for this to happen you need at least d bit changes. So as long as the errors are under d, you should be able to detect an error. So given this, can you guess how many errors a code word with distance d can correct? So the answer is d minus 1 by 2, because with these many number of errors, the received code word that is in error is still closer to the original code word than any other code word. Thereby you will be able to correct. Here is an example to illustrate these things. So here is a repetition code where when you want to transmit the bit 0, you transmit 0, 0, 0, and when you want to transmit the bit 1, you transmit 1, 1, 1. So this repetition code reminds me of Supandi joke in Tinkle. I don't know how many of you follow this book, but anyways, Supandi is a very innocent person who creates very funny situations. So here is the joke. So one day he is going in the bus and he asks for 2 tickets from the ticket conductor. This ticket conductor sees that he is traveling alone and he says, "Why do you want 2 tickets?" So Supandi tells him that if I lose 1 ticket, I will have another ticket. So this bus conductor thinks this guy is crazy, but anyway, for argument's sake, he asks, "What if you lose both tickets?" So Supandi says, "I have a bus pass." So that's repetition code in action. Thereby, in this case, we have m is 1 because it's only 1 bit, k is 2, so we are adding 2 redundant bits, and n is 3. So given that n is 3, there are 8, so n is 3, so there are 8 possible code words, of which how many are legal? Only 2. There are only 2 legal code words. Now given this, what is the Hamming distance of the code? So the Hamming distance is 3 because these 2 legal code words, if you do an XOR between them, that is going to turn out to be 3. You also notice that the code rate is 1/3, that is only 1/3 of the data stream has useful content. The others are all redundant. So given this, how many errors can this code detect and how many errors can it correct? So if you plug in the formula of d minus 1, this is going to detect 2 errors, and if you plug in the formula of d minus 1 over 2, you will see that it can correct up to 1 error. So what's happening here is that any of these received bits, so rather received code words, are going to be decoded as the bit 0, and any of these received code words are going to be decoded as the bit 1. Now if 0 were transmitted, in which case it is 0, 0, 0, if you make 1 error where let's say this translated into 0, 1, 0, this is still closer to this code because the Hamming distance is only 1. But if you made 2 errors, this may translate into 0, 1, 1. Now this is closer to 1, 1, 1. Thereby this will decode as 1. That is why you cannot correct 2 errors, but you can still detect it because you know that these are the only 2 valid code words and this does not correspond to either of them. Thereby you are able to detect this, but you cannot correct this because this is now closer to 1. This code as such is a very simple code and is not particularly useful. Its correction as well as detection capabilities are very poor, so you don't want such codes. So when you're designing codes, these are some of the considerations. You want to keep k to the smallest possible so that you can achieve high code rates. You want to keep the redundancy low. But at the same time, you want to maximize the Hamming distance so that your error correction and detection capabilities are high. At the same time, you don't want to design codes that are very complex because it's not easy to implement them. In other words, you want easy encoding and decoding, which will require minimal memory and processing time. So a lot of the research goes in achieving these goals. So as part of this course, we will focus on error detection algorithms. Some of these codes I'm going to cover shortly. And we will also focus on error recovery through retransmissions in the form of reliable transfer. We are not going to focus on error correction. There are many such codes, Reed-Solomon convolution codes, turbo codes, because these are typically used in wireless, which is again not the focus of this course. So here is a quick summary. So we saw that it is important to detect errors both for data fidelity as well as not wasting resources. Once you detect errors, you can recover from them either through forward error correction or through retransmission, and there are some inherent trade-offs here. So you need to do either FEC or retransmission based on the particular situation. We also looked at a framework for error detection and capability. Basically, we covered Hamming distance and what the capabilities of a code are in terms of error detection and correction. And we also looked at the design consideration for the algorithm that does error detection and correction. So going forward, we will cover error detection in detail.